now. So before I forget, share my screen. Okay, so we're live on YouTube right now. Okay, so let me go to the PowerPoint. Okay, so what we're going to talk about is nomenclature. How do we name compounds? And let me just say that there's a system that has been developed by chemists to name compounds based on its composition and vice versa. And this is a set of rules that is established by an organization known as the International Union of Pure and Applied Chemists. Let me write this down here. So the abbreviation for that, sorry about it. Keep forgetting to plug this in. Okay. All right, so the name of the organization is the Internet, whoops. Okay, why is this thing not writing? It's the Internet, oh Lord, what's going on here? This thing is not cooperating. It's the International Union, I'm using my mouse to write this, so please forgive me, of Pure and Applied Chemists. All right, that's my C there. Okay, so this is the organization that is responsible. At least I should say there's a division within this organization whose sole purpose is to come up with rules for naming compounds. And they meet, if I remember correctly, they meet every 2 or 3 years for this explicit purpose, all right? So all the rules that we're gonna learn concerning binary molecular compounds and other compounds we're gonna look at, these are rules that have been developed by this organization, all right? So let me go back to the PowerPoint here. And first we're gonna deal with binary molecular compounds. Binary molecular compounds are basically compounds that are made up of 2 non-metallic elements. And some examples are shown here. Carbon monoxide, nitrogen monoxide, water. Those are just a few of the examples. Hydrogen fluoride. These are just a few of the examples of what we call binary molecular compounds, right? Now, whenever we're writing the formulas for these compounds, we usually, well, not we usually, the standard is that we write the more metallic element first, followed by the less metallic element. Now, of course, they are non-metals, so there are no metallic elements. So you could look at it in terms of the electronegativity values. The one with the lower electronegativity value, that would be the one that is considered to be more metallic, and therefore that element will end up in the first place in the formula for the binary molecular compound, right? So carbon is less electronegative than oxygen, so therefore we put the carbon first, followed by the oxygen, all right, for example. Okay, so that's basically the standard convention that we follow when it comes to writing down the formulas for these compounds. Now, you might be wondering, how do you determine which one goes first? Well, you could memorize this chart, which I won't expect you to do, but you could also look at it in terms of the relative positions of the elements in the periodic table. So if you have 2 elements making up the compound, the one that is further to the left and above in the periodic table is the one that is going to be mentioned or written first in the formula. Or, as I said before, you could use the electronegativity tables. The one that is less electronegative would be the one that is written first. All right. So you know that formulas contain subscripts, and the subscript basically gives you the number of atoms present per molecule if you're writing the molecular formula for a compound. And here are some examples. So for example, in the case of water, there are 2 hydrogen atoms and 1 oxygen atom per molecule. And you can basically use that idea to interpret what these other formulas mean, all right? So subscripts will become important, especially when you're naming these compounds, as we're gonna see shortly, because the presence of the subscripts will be indicated in the name of the compound by using certain prefixes. So let's look at an example of 2 compounds, CO and CO2, all right? So if we were to name these compounds, we follow the convention that we said before. The carbon would come first, followed by the oxygen. Now, in the case of the first element, you use the full first name of that element, which is carbon, in these two examples. But for the case of the second element, you use the initial stem of the name of that element, and then you follow that up with IDE. So therefore, oxygen in these formulas become oxide, all right? Nitrogen becomes nitride, sulfur becomes sulfide, and there are others that I'm quite sure you can think of, right? So the ending of the name of the second element always ends with IDE when it comes to naming binary molecular compounds. Now, even though we have followed the rules so far, these are two different compounds, and therefore there must be something that we can do to distinguish between CO and CO2, right? Because they're two different compounds and therefore they can't both have the same name. And this is where the prefixes comes in. So these are the prefixes that are in common use when it comes to naming binary molecular compounds. And you should know this by now: mono for 1, di for 2, tri for 3, and so on, all the way to deca for 10. And there are more beyond 10, but for all purposes, we will stop at deca for 10, all right? So this is what we use to distinguish between these two compounds. So therefore, in the case of the first one, the name of that compound is carbon monoxide, and the name of the second one is carbon dioxide. So this is carbon dioxide because you have two oxygens here, and this is carbon monoxide because you have one oxygen here, all right? Now you might be wondering, what about the first element, right? Why is there no mono for the carbon here and here? Because there's only one carbon atom in each case. And the answer is that when the first element has only one atom reflected in the formula, then no prefixes are used, all right? So in the case of these two, the name of this one is simply carbon monoxide and not monocarbon monoxide, because there's only one carbon atom, and that's the first element mentioned in the formula. And the same thing is true here, all right? And you'll see that in these examples listed here. So for example, the name of this compound here is nitrogen monoxide. The name of this compound here is nitrogen dioxide. However, when you get to this compound, because you have two nitrogens, then you have to indicate the two using the prefix di. So the name of this compound will be dinitrogen trioxide. In this case, it's dinitrogen tetroxide. In this case, it's dinitrogen pentoxide. And then if you look at this example here, there's only one sulfur, which is the first element named here. So therefore we call that sulfur hexafluoride. And then this one is called iodine heptafluoride, all right? And therefore you can follow the logic for naming the others, all right? So some key things you need to remember here, right? The first element, you use the full name. The second element must end with IDE, ide. And you have to indicate the number of atoms present per molecule for each element using the prefixes, excepting if there's only one atom indicated for the formula or in the formula for one element, then we do not use any prefixes for that particular element. All right, so that's basically how we name binary molecular compounds. Now, the rules are a bit different when it comes to binary ionic compounds. But before we go into naming them, let's refresh our memory about how ions are formed. Ions are formed, of course, when atoms either lose or gain electrons, all right? So the positive ions are known as cations, the negative ions are known as anions, and therefore, here's an example. Sodium, when it loses one electron, forms a sodium ion with a +1 charge. And over here we have the chloride or chlorine atom, which when it gains an electron forms a chloride ion, all right? And therefore, in the formation of the ionic compound, the cation and the anion comes together to form your ionic compound, all right? So the monatomic ions are what we're talking about here. These are the ions that tend to lose or gain electrons to form, or these are atoms that lose or gain electrons to form these monatomic ions. And these are just some general statements about the type of ions that are formed. Group A metals tend to lose the number of electrons equal to their group number. So elements in group 1 tend to lose 1 electron, elements in group 2 tend to lose 2 electrons, and so on. And then non-metallic atoms usually gain electrons and have a charge equal to their group number -8. So therefore, elements in group 7 tend to have a charge of -1, 7 minus 8 is -1. Elements in group 6 tend to have a charge of -2, 6 minus 8 is equal to -2, and so on and so forth. Now, when it comes to the group B elements, the transition elements, it is not possible to predict the type of charges that they will display, all right? So in group A, you can to some extent, to a great level of accuracy, determine or predict the charge on their ions. You cannot do that, however, for the elements in the transition elements. And another complication is that those elements tend to, in some cases, form multiple charges. So for example, you can have, and I think I have this on the next slide, you can have, for example, cobalt forming the ion with a +2 charge and an ion with a +3 charge. Copper can form an ion with a +1 charge or +2, and so on and so forth. So in this region here, we have that possibility. There are some examples outside of this region as well, where elements can display more than one charge. For example, lead. It's not shown here, but lead can have a +2 or +4, and the same is true for tin. It can have a +2 or +4. So there are instances where some elements can form ions of different charges, all right? So how do we determine the names and formulas for the compounds? The key thing you need to remember is that when ionic compounds come together, they basically form a neutral compound, which means that the total number of plus charges must be equal to the total number of negative charges. So in the case of the formation of sodium chloride, for every one sodium ion, there will be one chloride ion, because the sodium ion carries a +1 charge and the chloride ion carries a -1 charge. So therefore the charges will cancel out, and therefore the formula for the compound will be NaCl, and the name of this compound will be sodium chloride. And if you look to the right on the screen, you'll see basically how sodium chloride assembles itself to form this gross structure. You'll see that there are no discrete units of sodium chloride. There's no such thing as a molecule of sodium chloride. Basically what you have is what is called a crystal structure, where you have repeat units that just go on and on and on, where each repeat unit has the same arrangement, and it's a highly ordered arrangement, all right? Okay, so that's a relatively simple example. And there are some other examples that are shown here. So just to give a few, let me see if this thing is working now. I hope it's working now. Okay, for some reason it's, let me try this one here. Okay, I don't know why this is not behaving itself. It was working a while ago. Let me try this. Okay, now it's working. All right. So let me just do a couple of examples. So let's say you're given copper. Oh no, what's going on here? Oh, I don't know what's going on with this. All right. So let's say, for example, you're given copper. I'm using my mouse here, so please forgive me again. Copper 2 nitride, NiTrIDE. And let's say you're asked to write down the formula. So you could go to the tables I've provided for you. In fact, there are 3 pages in the table that you can look at to determine the formula if you're given the name of the ions. So in the case of the copper 2, that is Cu2+, and the nitride is N3-, all right? So in order to get the charges canceled out, you'd have to multiply this by 3, you have to multiply this by 2, and then when you put them together, you're going to get Cu3N2, and that would be the formula for copper 2 nitride, all right? So that's basically how, if you're given the name of the compound, which is this, that's how you get to the formula for the compound. And of course, I'm quite sure you should be able to figure out how to do the reverse. Okay, continuing. Okay, wrong. Okay, no, that's not it. Okay, okay, so this slide gives you some other ions that are not monatomic, they are polyatomic. And the polyatomic ions are those that basically consists of a collection of atoms and that as a unit carries a charge. So for example, the carbonate ion is an example of a polyatomic ion because the ion contains 1 carbon and 3 oxygen atoms, and as a unit, it carries a -2 charge. Now, when you're dealing with these particular ions, you have to be careful, especially when you're writing down the formulas. So let me get back to this again, and let me do a new page. So let's say, let me do this again. Let's say you're given, I don't know, magnesium, nitrate. Let's do that one. All right. So the formula for the magnesium ion is Mg2+. You can look that up, Mg2+. And the nitrate ion is NO3-. So to make sure that the charges are canceled out, you're going to need 2 of these. Now, here is how we deal with polyatomic ions when writing down the formulas. Mg, then open parentheses, then NO3, whoops, NO3, 2, all right? And that would be the formula for magnesium nitrate. So the key thing here is that the polyatomic ion, if you have more than one of them, you have to indicate that there is more than one of them by putting the formula within parentheses and then putting that number, in this case 2, outside the parentheses, all right? So that's basically how we deal with polyatomic ions. Now, so these are just some other examples you can look at. And that's it as far as polyatomic ions are concerned. Now, here is a group of compounds that I don't think you'd have met before in your introductory chemistry or high school chemistry. These compounds are known as hydrates, and they're very unique because basically these are ionic compounds, but in addition to the ionic unit, you also have a fixed number of water molecules associated with each formula unit, all right? So here are 2 examples. You have this compound here, BaCl2, and then you put a dot and then 2H2O, all right? So basically what this is saying is that for every unit of barium chloride in this compound, we have 2 water molecules. And then here, same thing, copper CuSO4 dot 5H2O, same idea, all right? So these are very interesting compounds. For one, let me go back to this again. When you get this compound here, I'm going to use the barium chloride example in this case. So BaCl 2.2H2O. All right. Now, when it comes to naming these compounds, you name this part just like you would ordinarily do, as we learned before. So this is barium chloride. But now you have to indicate the number of water molecules. And in this case, it's going to be dihydrate. So you use a prefix di. I'm sorry about this, folks. I'm so sorry. Di, and then hydrate. All right. So we use a prefix di to indicate that there are 2 water molecules, and we indicate the hydrate, which indicates the presence of water. All right. Okay. Seems as if my tablet is working. Okay. So let me try with the other one. Cu. Okay. I guess it's not working. Okay. Stick to the mouse. So the next one is CuSO4 dot 5H2O. Okay, so in this case here, the name of this compound would be copper 2 sulfate pentahydrate. Okay, I'm really getting bad at this. Okay, so that's the name of this compound, copper 2 sulfate pentahydrate. Again, the penta indicates the number of water molecules, and the hydrate indicates, again, the presence of the water molecules, all right? So that's basically how we name these compounds. Another interesting thing about these compounds, let me just erase something here. Another interesting thing about these compounds is that you can easily remove the water molecule by simply heating the compound to 100 degrees. So for example, in the case of the first one right here, this is H2O. If you heat it to 100 degrees Celsius, then you're gonna end up with BaCl2 plus 2H2O, all right? So this form is called the hydrated form, as we said before. This is hydrated. And this form here is called the anhydrous form, ANHYDROUS, all right? So when you heat the hydrated form to 100 degrees, heat it long enough, then you're going to end up with the form without the water, which is called the anhydrous form. And in some cases, you'll see a change in appearance. Now, in the case of barium chloride, both the hydrated form and the anhydrous form are white in color, but if you look closely at the different forms, you'll see that the hydrated form has a more crystalline appearance, while the anhydrous form will be more powdery in appearance, all right? In the case of the copper 2 sulfate, when you heat it, well, originally the color is blue. In fact, going back to the PowerPoint here, you'll see that we have the blue form here. This is the hydrated form of copper 2 sulfate. And if you heat it to drive the water off, you're going to get the white anhydrous form of copper 2 sulfate. And as you can see here, you can easily reverse that process. If you add water to the anhydrous form, you're going to get back the blue form, which would be the hydrated form. All right, so that's basically how hydrates behave. All right, okay. Another group of compounds that we need to talk about are acids. And these are the characteristics of acids that are listed here. The first one, it says that acids have a sour taste. Now, let me just say this while I'm at it. Please, 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 if you're in a lab and you want to find out that something is acidic, please do not taste it. That is not the way we do things in the lab. We carry out tests such as what is indicated here in the second property here. Acid turned blue litmus paper red. So basically, if you want to test for the acidity of a substance, you take blue litmus paper and dip it in the acid and look at the color change, and you see the color changes from blue to red. Acids will react with some metals, the more active metals, to form hydrogen gas. And another property is that acids will neutralize a base. We call that an acid-base reaction or a neutralization reaction, all right? So these are the properties of acids. And then we have the bases and their properties. Bases, they taste bitter. Again, please do not taste a base to make sure that it's a base. You test the base by using the red litmus paper. If it turns blue, then you know that you're dealing with a base. Another property of bases is that they feel slippery on the skin. Again, I would not recommend that you carry out this test to determine that your substance is a base, but this is a very interesting property, because what happens when a base comes into contact with the oils on your skin, it actually converts the oil to soap. So therefore, what you're feeling, that slippery feeling that you'd feel if it gets on your skin, that is basically soap being formed, all right? And the final property here is that bases neutralizes acids, all right? So those are the properties of acids and bases. Now, there are several definitions of acids. The one that we're going to look at today, and bases, I should say. The one that we're going to look at today is the definitions according to this guy here, Arrhenius. And according to Arrhenius, acids are compounds that when dissolved in water produces hydrogen ions and some other ion, all right? While bases are compounds that when dissolved in water form hydroxide ions and some other cation, all right? And as I said before, the reaction between an acid and a base will form a salt and water, and that reaction is neutralization, all right? So according to the Arrhenius concept, an acid such as hydrochloric acid will react with a base such as sodium hydroxide to form a neutral solution. Now, this is not 100% true, but we won't complicate things now. But suffice to say, when you get to general chemistry 2, you're going to learn about the fact that there are some salts that are acidic and some salts that are basic, all right? So in this particular case, we can figure out what the formula for the salt is. The salt comes about as a result of the positive part of the base combining with the negative part of the acid, and the rest will combine to form water, right? So in this particular case, the salt that is formed is sodium chloride, and the other product is water. And this is true for any acid-base reaction. Basically, when the acid reacts to the base, a salt is formed and water is formed, and you can figure out the formula for the salt using the idea that we just outlined, the positive part of the base coming together with the negative part of the acid to form the salt. Okay, I'm going to take a break right here. Give me about a minute and I'll be right back. Okay, folks, sorry about that. So let me continue our discussion of acids. In particular, how do we name them? Now, there are a couple of types of acids, and let me see if I can get this thing working because this is really annoying me. Let me do this again. I don't know why this is acting up. Okay, I think I figured it out. Okay. No, I guess I didn't. Okay, so in naming acids, we have binary acids. All right, binary acids is one group of acids, and then there's another type of acids known as oxyacids. All right, so what I'm going to do is I'm going to talk about how do we name these acids, because the rules are different for these types of acids. All right. Now, in the case of binary acid, I'm just going to use one example right here. Now, this compound I'm about to write is hydrogen chloride, HCl gas, right? Hydrogen chloride exists as a gas. If you add this to water, it becomes HClAQ, all right? The name of this, as I said before, is hydrogen chloride. And when it's added to water, the resulting solution is called hydrochloric acid. So you can see how the name is transformed as you go from hydrogen chloride to hydrochloric acid. Basically, we start off with hydrochlor, and then the rest of the name is ending with ic acid. And this is basically how we name these acids, these binary acids. You start off with hydro, the stem of the name of the element other than hydrogen in the acid. And then we follow that up with ic acid, all right? Here's another example. Suppose you're given H2S, aqueous. Sorry about this, folks. All right. The name of this compound is hydrogen sulfide. Okay, and when you add this to water, this becomes, oh, by the way, this should be gas. I'm sorry, this is gas, all right? When you add it to water, it becomes H2S, aqueous. And the name of this is hydrosulfuric acid. Hydrosulfuric. Sulfuric acid. Okay, so that's basically how we name these binary acids. So these are just two examples, and I have some others listed in this table right here. So this is hydrochloric acid. This is hydrosulfuric acid. Those are the two examples I showed you earlier. And there are some others as well, which are not listed here. You can have hydrobromic, hydroiodic, and so on and so forth, all right? So that's basically how we name binary acids, right? The binary acid starts with hydro and end with ic. And in between, you're going to have the stem of the name of the other element, the non-hydrogen element present in that acid. So hydrochloric, hydrobromic, hydroiodic, hydrosulfuric, hydrophosphoric, and so on and so forth, all right? So that's basically how we name binary acids. Now, when it comes to the oxyacids, it depends on the anion from which it is formed. Let me try to explain what I mean by that. So let me go back to this again. And this time I'm just going to stick to writing with the mouse. Okay, so let me start off with NO2 minus, right? Now, if you look this up in the tables I provided, you'll see that the name of this ion is nitrite ion. All right. Now, if you add one hydrogen ion to it, you're going to get a formula for the corresponding acid, which would be HNO2. And the name of this acid is nitrous acid. All right. So please note how the name changed. Basically, to get from NO2 minus to HNO2, the ending here, ITE ending, is replaced with OUS acid. All right. So ite becomes OUS acid. Nitrite becomes nitrous acid. Here's another example. SO3, 2 minus. Now in this case here, we needed to add 2 hydrogen ions because there are 2 negative charges on the sulfide ion. So the formula now becomes H2SO3. This is called the sulfide ion. This is called the sulfurous acid. All right, so again, you see the name change or the modification of the name from ITE to OUS acid. All right. So that's basically how we deal with that change from ITE to OUS. Now, here are some other situations where instead of the ITE ending in the corresponding acid, we have, or in the anion, we have ATE ending. So let me give a couple of examples of that. This ion here, NO3 minus, this is called the nitrate ion. To get the corresponding acid, we add 1 H plus, and the formula is H plus, and the formula becomes H NO3. And the name of this acid is nitric acid. All right. So in this case here is CID. Okay. So in this case here, the ATE ending is replaced with ic acid, right? So that's how we deal with the naming of acids formed from anions whose name ends with ATE. We get the formula by adding the number of hydrogen ions needed, and then we convert the name ending from ATE to ic acid. Here's another example. This ion here, SO4 2 minus, is called sulfuric acid. I'm sorry, sulfate ion. And in this case, you need to add 2 H plus. So this becomes H2SO4. And the name of this acid is sulfuric acid. All right. So that's basically how we name these acids. Again, you see the ATE ending is replaced with ic acid. All right. So that's basically how we name oxyacids. Okay, now there's one particular acid that does not fit into the category of binary or oxy. And that acid is this acid right here, HCN, hydrocyanic acid, all right? It is not a binary acid because it has 3 atoms or 3 elements, and it's not an oxy acid because there's no oxygen. So this begs the question, how do we arrive at this name of cyanic acid, hydrocyanic acid? So let me write this down, hydrocyanic acid. Well, according to the IUPAC folks, what they decided to do was to treat this as a binary acid, all right? So basically, it's basically treated as if hydrogen is one element and CN is treated as another element, even though C and N are 2 separate elements, right? So basically, we use the rules for naming binary acids for naming HCN, and that is called hydrocyanic acid. And that acid is formed from a gas known as hydrogen cyanide, HCN. And this is a gas you don't want to be in the same room with if you want to live. Very toxic gas. It reduces the capability of the oxygen of the blood in the circulatory system to transport oxygen. Anyway, so this is called hydrogen cyanide. Hydrogen cyanide. CYANID. Okay, so that's a very unique acid in terms of how we name it. Okay, so what next? Let's go back to the PowerPoint. And bases. So we have talked about acids. So now we're going to talk about naming bases. How do we name bases? Well, according to Arrhenius, as we said before, a base is a substance which, when added to water, form hydroxide ions. Now, you can have ionic compounds which are bases, such as sodium hydroxide. So sodium hydroxide, when you add it to water, forms hydroxide ions. But you can also have molecular compounds, such as ammonia, which when added to water forms a hydroxide ion, as seen in this formula here. Ammonia added to water gives you ammonium hydroxide, which has hydroxide ions in an aqueous solution. So these are just some examples of bases. And I think on the next page, I have, formulas for salts and names of salts. So let me just finish up with this here. That's basically it as far as bases are concerned. In terms of their names, it's basically following the same rules as we did earlier for ionic compounds. And then now for salts, naming these salts is basically the same as we saw before. And for us, it's very simple. All we have to do is look for the names of the anions and cations and put it together. And that's how we end up with names of these compounds, right? So you have examples such as sodium sulfide, sodium perchlorate, sodium nitrate, and so on. So it's a very easy exercise to name these compounds. All right. Okay, we're not going to continue with organic compounds in this chapter. I leave that for you guys who plan to do organic chemistry later on if you have to. So that basically signals the end of chapter 2. Are there any questions you want to ask before I move on to chapter 3? Any questions? Any questions?
I don't think so.
Okay, so let's move on to chapter 3, which deals with, for the most part, stoichiometry. And again, this is something that you should be familiar with from your high school introductory chemistry. Stoichiometry is basically that area in chemistry which deals with the quantitative relationships between substances that are reacting with each other. So therefore, what will become important when it comes to stoichiometry are concepts like the mole concept, how to determine the molar mass of a compound, how to balance an equation, how to establish the mole ratios between different substances in an equation. And then from there, you can move on to doing some stoichiometric type problem. So again, a lot of review will be involved in this chapter. So I'm just going to go through this rather quickly. So let's start talking about the molecular mass. Very simple concept. It is simply the sum of the masses of the atoms represented in a molecular formula. So for example, in the case of H2O, you simply multiply the molar mass or the molecular mass or the atomic mass, I should say, of hydrogen by 2 and add it to the value for oxygen. And that will give you the molecular mass of the compound. Very simple. And you can do this for small molecules like water and large, humongous molecules, all right? Here are some other examples. Sulfur dioxide, same idea. And then even a larger molecule like glucose, same idea. The only difference is that the numbers will be larger. In the case of glucose, when you add these all up, you're going to get 180 atomic units, all right? Now the formula mass is basically the same thing. The only difference is that we apply it to the formula for an ionic compound, right? So if you have an ionic compound like sodium chloride, remember now, ionic compounds do not exist as molecules. So basically we're using the empirical formula for the compound. And therefore, when we add them up, in the case of sodium chloride, this is what we get, 58.44 atomic mass units, AMU, all right? So it's basically the same thing as the molecular mass, but we apply it to the formula unit for an ionic compound. Then we get to Avogadro's number, right? Which is basically the number of items in 1 mole of anything, all right? So that number, of course, you should know is equal to 6.02 times 10 to the 23. And then we get to the definition of a mole. A mole is an amount of substance that contains as many elementary entities as there are atoms in exactly 12 grams of the carbon-12 isotope, all right? So that's basically where the mole concept comes in. Now, the mole concept can be literally applied to anything, all right? But of course, in the chemistry, we apply it to small particles such as atoms or molecules or ions, etc. All right?
Oh, this is sort of an aside, but I did read a sort of an article about what would happen if you had 1 mole of moles. And it was pretty fun.
Yeah, and it's a huge number. Let me see if I have it here, or maybe I have it somewhere else. I remember reading, or I had something which says, if you had 1 mole of, I forgot what it was, it would circle the Earth twice or 3 times or something. I don't remember exactly. I'd have to look it up. But as you can imagine, it's a very huge number. And necessarily it has to be, because of course we're dealing with small particles. And if you have a significant number of, if you have a significant amount of a substance, then the number of particles within that substance would be huge. Okay, so if you look at this reaction here between carbon and oxygen to form carbon dioxide, then basically at the molecular level, we can say that one carbon atom will react with one oxygen molecule to form one molecule of carbon dioxide. So that's true at the molecular level, and we can extend it to the level of moles, right? So if it's a 1-to-1-to-1 ratio between the carbon, oxygen, and carbon dioxide, then basically when it comes to Avogadro's number, it will be the same ratio, which would be 1 mole to 1 mole to 1 mole. So if you have a balanced equation, the coefficients represent not only the number of molecules or formula units, but it also represents the number of moles, relative number of moles of the substances involved in the reaction. And that is demonstrated here, where you have 1 mole of carbon, 1 mole of oxygen gas to form 1 mole of carbon dioxide, right? But you'll notice here that the masses are different. You have 12.011 gram of carbon, you have 31.9988 grams of oxygen in 1 mole, and you have 44.010 grams of carbon dioxide in 1 mole, right? So basically the moles would be the same, but the actual masses would be different, right? So these are what we call the molar mass, which we'll talk about later on. And another thing I want to highlight about this equation as well is that this, again, demonstrates the law of conservation of mass, because if you add up these two reactants here, if you add up their masses, you'll see that it's equal to the mass of the product, right? So therefore, matter is not created nor destroyed in this reaction, as it is the case of all reactions, all right? So speaking of molar mass, I talked about molar mass just a while ago. The molar mass, by definition, is a mass of 1 mole of that substance. And it turns out that numerically speaking, the molar mass of a substance is equal to the atomic mass, if you're dealing with elements, molecular mass, if you're dealing with molecules, and formula mass, if you're dealing with ionic compounds, right? So numerically speaking, the molar mass and the atomic mass, molecular mass, or formula mass would be the same thing. The difference between them would be the units, right? Now, the units of molar mass is grams per mole, right? While the unit of atomic mass, molecular mass, or formula mass would be AMU. So for example, if you go to the periodic table and you look up the atomic mass of sodium, then that would be 22.99 AMU. But the molar mass of sodium is 22.99 grams per mole, all right? Same is true for molecules such as carbon dioxide. The molecular mass of carbon dioxide is 44.01 AMU, but the molar mass of carbon dioxide is 44.01 grams per mole, all right? So numerically they're the same, but the units are different, all right? So very important concept that you need to understand and appreciate. So how do we calculate, how do we do calculations involving molar mass? Well, sometimes you're asked to find the mass of a substance if you're given the moles or vice versa. And therefore, what you can do is express the molar mass as a conversion factor like this, right? You can have it expressed as the mass in grams of a substance over 1 mole or the other way around. And of course, which one you're going to use is dependent on the type of conversion that you're trying to achieve. So here's an example. Suppose you're given 0.250 moles of ammonia and you're asked to find the grams. Then what you do is that you first find the molar mass. They gave you the formula, so you look up the molar masses of the different elements in the periodic table and you add them up, which is what is done here. And you end up with the molar mass being equal to 17.024 grams per mole. And then you do your setup. So we start off with the 0.250 moles of ammonia, and then we express the molar mass this way. And the reason why we express it this way, is because you have the 1 mole unit down here, which will cancel out with a mole of ammonia down here. And up here, you're going to have grams of ammonia. So when those two cancel out, you'll be left with grams of ammonia. And all you have to do is do your number crunching, punch your numbers in the calculator, and you're going to end up with your answer being equal to 4.26 grams of ammonia. So that's basically how you do that if you're converting from moles to grams. And of course, if you understand this, then you should be able to understand how to go from grams to mole, all right? So that's basically how that is done. All right, what time is it? Let's see. Okay, we got some time. So let's talk about percent composition. Now, percent composition is a very easy concept to understand. In principle, I'm going to use this diagram here to illustrate the whole idea, excuse me, of percent composition. So here we have 6 blocks, different color. We have 2 blue blocks right here, and we have 4 orange blocks. So we can find out the percentage of the blocks that are blue, so or orange. So that would be 4 divided by 6 times 100%. That would be 67%. And then for the blue, I don't know why they have green here. It should be blue. For the blue block, the blue blocks, it would be 2 divided by 6, which would be 33%. All right. So that's basically how you determine the percentage of blocks present in this diagram. It's the same idea when it comes to compounds, right? Basically, what you're going to do is take the ratio of the total mass of a particular element and divide it by the total mass of the compound, and that will give you the mass percent of that particular element in the compound. All right. So the example we're going to use here is this compound, which is called butane. As you can see, the formula is C4H10. So basically, to get the percentage of carbon, all we have to do is take the molar mass of carbon, which is 12.011, and multiply it by the number of carbon atoms represented in the formula, and that gives you a total of 48.044. Then we take that and divide it by the total mass of the compound. Now, to get the total mass, we have to take the other element, which is hydrogen, take its molar mass, multiply by 10, and add it. Well, when we multiply, we get 10.079 grams, and then we add it to the mass of the carbons, and we get the total mass of the compound. Now, to get the percentage of carbon, we take the total mass of carbon divided by the total mass of the compound times 100%, and that will give you the percentage of carbon, right? And if you want to find the percentage of hydrogen, then we take the total mass of hydrogen divided by the total mass of the compound, multiplied by 100%, and we get the total percentage of hydrogen. So that's basically how we determine the mass percent composition. All right. Any questions about this? Any questions about the mass percent composition? Okay, so let's talk about the difference between the molecular formula for a compound and the empirical formula. And if I remember correctly, we talked about this before, but we're going to get into more details as to how we can determine them using calculations based on empirical mass and molar mass and percent composition data and all of that good stuff. Okay, so just to remind you, the empirical formula is the simplest whole number ratio of the elements in a compound. So if you take glucose, for which the molecular formula is C6H12O6, well, the empirical formula would be the simplest ratio, which would be CH2O, because what this tells you is that the ratio of carbon to hydrogen to oxygen is 1 to 2 to 1, all right? So that's the difference between the molecular formula and the empirical formula. Another thing you need to realize is that to get from the empirical formula to the molecular formula, you have to multiply the empirical formula by some integer, right? And we're going to learn later on how do we get that integer so that we can do that conversion from the empirical formula to the molecular formula. Okay, you know what? I think I'm going to stop here because, and only because my tablet is not working too well, because I really want to do this example step by step so that you can understand how to solve a problem like this. Basically, what this question is done is given you is the percentage of different elements in the compound. And based on that information, you're asked to determine the empirical formula for the compound. And it's a step-by-step process, which it's very important that you understand. So what I'm going to do is stop here for today. And unless there are any questions, that's the end of our class for today. So are there any questions? Any questions?
Not from me. I'm good.
No questions?
Have you talked to the testing center about how?
Oh, yes, thank you. Yes, I did. Okay, so here's the situation. I called Ocala again, left a message, and somebody emailed me back. And basically what they're saying is that no pen and paper tests will be allowed or done in a testing center, which is what I was hoping for. So basically, as far as the tests are concerned, basically it would be take-home tests for you guys, right? I'm just going to post the test online and give you a time period within which to complete it, and that's it. You scan it and upload it and receive it and grade it. So that's basically what's going to happen. I was going to post an announcement about that, but since you asked, that's basically where we are at as far as the testing center is concerned.
Oh yeah, I have a question. So for one of the assignments, I forgot which one, even if it was for a lab, I'm not sure.
Mhm.
But I used a digital pen and paper thing for it. Is that all right? Instead of just scanning and sending it in?
Yeah, I guess that's okay, as long as I can see it and as long as I can make it out.
Yeah, because I just don't want to keep printing out stuff and scanning it. And
Yeah, I understand. Yeah. Yeah, if it's legible and clear and all of that, then yeah, I have no problem with that.
As long as it's a PDF.
That's important, right? PDF. Very important. Okay, any other questions? Okay, if there are no other questions, that's basically it for today. And I'll see you guys next Tuesday, all right?
All right. Take care.
All right, take care. Have a good weekend.
You too.
Mhm.
Bye.
All right, bye.